All right, I'm going to go through lesson 7.5 with you. We're going to take everything that we learned in 7.2 about equilibriums and equilibrium constants, and we're going to take that and build on that by doing a few more examples. We have 5 examples in total in this lesson, and I'm going to do each one as one video. So hopefully that breaks it down into 5 different sections. So just as a recap, if you remember from 7.2, when we learned about equilibrium constant, we learned that the equilibrium constant for any reaction, let's say this hypothetical one is the one we're looking at, equilibrium constant is K, and you can find out K by taking the concentration of each of the products and raising them to whatever the coefficient is. So the exponent is going to be the coefficient, the concentration of the other product, and raising it to whatever the coefficient is. And the same thing for the reactant. So you always want your products to be on top and your reactants to be on the bottom. So this is your general formula for the equilibrium constant. And we looked at this and we looked at ice charts in 7.2. Let's take a look at this first example and see how this is going to be different from what we did in the previous lesson. So in this particular question, they're telling us that the equilibrium constant for this particular reaction is 16. Remember that our equilibrium constant does not have a unit, so that makes sense. It's just the value 16. Initially, you have 0.22 moles per liter of PCl3 and Cl2 gas, and they're placed in a container and allowed to reach to equilibrium. We need to find the equilibrium concentration of each of these gases. So what I'm going to do is make an ice table. And remembering from last time, our ice table has our initial concentrations, our changes, and the concentrations at equilibrium. So our initial concentration for PCl3, as we were told in our question, is 0.22. That is moles per liter, but just in our ice table, I'm not going to write the units. It just makes it easier for me. And we also have 0.22 moles per liter of Cl2. We have 0 PCl5, so we're not starting off with any product. So we don't know anything else in this question other than the value of K. So what I'm going to do is I'm going to assign values for the change. So I know that whatever change occurs for the reactants, right, if it's reducing to reach equilibrium, that is going to be gained by our product. So this is going to be plus X. And because the mole ratios are 1 to 1 to 1, I'm just going to write it as minus X, and plus X. So at equilibrium, my equilibrium concentrations of PCl3 is going to be 0.22 minus X. I'm going to put a little bracket there. For Cl2 is going to be the same. Maybe I can use a different color so it's a little bit more obvious. 0.22 minus X. And for PCl5, it's just going to be the value X. Okay, so I have made my ice table and I figured out, even though I don't know the equilibrium concentrations for each of these reactants and products, I have an expression that can help me and I can use that to find it later on. So what I'm going to do now is write my equilibrium constant equation, right? So my K is equal to, and because I have my reaction, I'm going to use that. And I know that my products go at the top, so PCl5, concentration of that, divided by the concentration of PCl3 times the concentration of Cl2. What I'm going to do now is plug in everything that I know. According to my question, I'm given that K is equal to 16. So I'm going to use that and plug that in as well. So 16 is equal to, and PCl5, the equilibrium concentration for that is X. So I'm going to write X at the top, divided by the concentration of PCl3, which is 0.22 minus X, 0.22 minus X, times the concentration of Cl2, which also happens to be 0.22 minus X. All right, what I'm going to do is multiply these two brackets together. And in order for me to do that, if you remember from the last lesson, we have to do FOIL. And when I do that, I'm going to end up with 16 is equal to x divided by, and I'm going to multiply the first two together to give me 0.0484 minus 0.22x minus 0.22x plus x squared. So I've got this really long expression here. I'm going to try and simplify it. So 16 is equal to x divided by 0.0484 minus 0.44x plus x squared. Okay, this is as far as I can simplify it. What I'm going to do is take this whole expression that's on the denominator. It's being divided at the moment, so I'm going to take it over to the other side and multiply it. And when that happens, I'm going to change my color here. 16 times 0.0484 minus 0.44x plus x squared is equal to x. So keeping like terms to one side, I'm going to move everything over and simplify it to a point where I will get 0.7744 minus 8.04x plus 16x squared is equal to 0. So maybe what you can do is pause the video there and confirm that when you do simplify this and make sure all the like terms are on one side, you do end up with this particular statement here. Now this can easily be used in our quadratic formula, right? We know that this is going to be, ooh, that is way too big. We know that this is going to be our A value, this is going to be our B value, and this is our C value. So using our quadratic formula, which is negative b plus or minus square root of b squared minus 4ac over 2a, I can solve for the value of x. And when I solve, I know that there are two different possibilities. So I get the answer x is equal to 0.37, or I can get x is equal to 0.13. Now, usually what happens with the quadratic formula is you have one that's positive, one number that's a positive value, and the other that's a negative value. And for us in chemistry, the negative value is usually the one that we discard. But in this case, I've got two different values that are both positive. But I really want to ask myself, do both of these values make sense? So if we take a look at our initial ice table, we know that our concentration that we started off is 0.22. So if you take a look at the numbers that we have here, I've got 0.37 and 0.13. If I have 0.37, it doesn't make sense that the concentration of PCl3 and the concentration of Cl2 will reduce more than there was to begin with, right? We had 0.22 moles per liter. Can you take away more than 0.22 moles per liter? No, right? Because 0.37 is more than the initial concentration that we started off with. We only had 0.22 moles per liter to begin with. So it does not make sense for it to reduce by 0.37. So picking a different color here, this does not make sense, right? So even though both of these values are positive, only one of them is really going to work out to be our final answer, right? So we want to make sure that when we have more than one possible answer, we choose the one that's most appropriate. So because we have this, we can easily figure out our concentrations at equilibrium because we know the value of x, and we're going to use that as 0.13. So I know that the concentration of PCl5, at equilibrium is equal to x. And we just found out what x is, which was 0.13 moles per liter. We also know that the concentration of Cl2 is equal to 0.22 minus x. And 0.22 minus 0.13 gives me 0.09 moles per liter. Now, I'm not using 0.13, I'm using the full number that I got when I solved for the quadratic equation, right? So if you don't use the rounded version here, use the full number so that you can end up with the correct answer. One more thing. So here's why it didn't make sense for us to use that other answer, right? It didn't make sense for us to use 0.37 because if I do 0.22 minus 0.37, I'm going to get a negative value in the concentration, which doesn't make sense for us. So similarly, I can use this to find PCl3, which is 0.22 minus 0.13, which is x. Maybe I'll just write that as x. And I end up with 0.09 again. Again, I'm not using the rounded number, which is 0.13. I'm using the full number that I got at the end of the quadratic equation, so I can solve for the equilibrium concentrations for each of these entities. Okay, that was our first example.